Okay, this is the third time I've made this video because I keep screwing up. So, third time's hopefully the charm here. We're going to solve linear inequalities, and they're going to have one variable. So I know that, lines can have two variables, but these inequalities will have one variable. So, a couple of recalls. Previously, when we were solving equations or equalities, we had the additive property of equality, and that said that we could add or subtract the same amount from both sides and it would still be equals. And I'm going to paraphrase to this. So that property, again, said we could, so it wouldn't be the same equality. It would be like we started with 7 equals 7, we added 2 to both sides, and now we have 9 equals 9. So it maintained the equals if we add the same amount on both sides, right? Balance it. And then we also had the multiplicative property of equality. So multiplicative property of equality. And that said we could scale it up or scale it down. Except, of course, that division by 0 is off limits. Yeah, it has chaos written in it. Example 1, and by chaos I mean I'm just going to leave it. Classify and evaluate. Classify quadruple x and then add 5 as an expression, equation, or neither. Well, look at here. I accidentally told you the answer within the question as long as you're reading. So this is an expression. And evaluate it when x is equal to the quantity 3. So if we know that x is 3, then we quadruple it and add 5. And we get 17. So when x is the value 3, quadruple it, add 5 is 17. Number 2, classify 3x minus 7 equals 2x plus 6 as an expression, equation, or neither. Well, we see this happy equality here, this equal sign, and that turns it into an equation. Is it true when x equals 3? Well, let's work it out. Triple the 3, subtract 7. That would be 9, take away 7, 2. Double the 3, add 6. Double 3 is 6. Add 6, you get 12. And nope. No can do. When x is 3, 2 does not equal 12. So it is not true that 3x, triple it, deduct 7 is equal to double it, add 6. Nope, not the case. Classify 4x minus 7 is less than x plus 10 as an expression, an equation, or neither. Well, it's neither. An expression doesn't have a relationship symbol. An equation has a relationship that they're equal. And this one actually is telling us that one is less than the other. So it's actually an inequality. Is it true when x equals 3? Okay, well, let's quadruple 3, take away 7. So quadruple the 3, we get 12. Take away 7, we get 5. Take the 3 and add 10. 3 add 10 is 13. 5 is less than or to the left of is lower than 13 for sure. So is it true? Yes. Yes. They got the symbol correct when x is 3. So when x is 3, yes, less than is maintained here. And now we didn't test for other values like 4, 5, -6, -100, whatever. We only tested for this one value. So it could be true for some other values, and it could be false for some other values. We just didn't test them. Example 2. Is it still an inequality? Okay, let's check this out. Number 1, true or false, 16 is greater than or to the right of 4. And the answer is true. Add 2 to both sides of number 1's inequality. Well, 16 plus 2 is 18. 4 plus 2 is 6. 18 is greater than 6. Is it still a true inequality? Yes, and it's the same. Same is true. Yeah, same inequality is true as it was in the beginning. Number 3, subtract 10 from both sides of number 1. Well, 16 take away 10 is 6. 4 take away 10. Okay, let's suppose we're at 4 degrees Fahrenheit and it drops by 10. That means we're at 6 below. 6 below. 6 is definitely greater than -6, even when we think about temperature. So, and now, after subtracting 10 from both sides of the true inequality in number 1, it appears that we have the same inequality and it is still true. So, same inequality is true here as well, after even deducting. So I'm going back to this, like adding and subtracting the same amount of both sides, but now it's not an equals, it's an inequality. And I'm seeing that the same is working out here. Okay. Number 4 says multiply each side of number 1 by 3. Okay, well, here's the thing. Number 1 was the inequality, so just to make sure we have this jotted down correctly. That was the inequality in number 1. And it says triple it. Let's magnify all of this. If you're wondering what I'm doing, my purple's on the fritz, so I had to get a new purple. Okay. All right, let's triple it. Well, 3 10s makes 30, and 3 6s is 18. So this is 48. And triple the 4, and we get 12. And 48 is greater than 12. So again, I see that the same inequality is holding true. I want to mention right here that if we magnify or we scale everything up by 3, what happens to the distance here? So 16 and 4 are 12 apart, and then if we magnify or scale up by 3, 48 and 12 are 36 apart. So just to give that a little bit of a, you know, like see it and think about it type of thing. Let's multiply the left and right side of number 1 by -2. Okay, well, 2 sets of 16 is 32, but now we're doing opposite. And 2 sets of 4 is 8, and it's the opposite. And now I see that, like, if we're doing, maybe this is debts, right? You owe to 2 different people $16. Now you owe $32. Well, owing through $32 is actually that's more in debt or lower than or to the left of or less than owing $8. So here, let's see what, well, we actually reversed the inequality because -32 is less than -8. We had to reverse to be true. So we reverse the inequality in order for this to be true. Okay. Now let's divide each side of -1 by -4. Okay. I'm sorry, divide each side of 1 by -4. 16 divided by negative 4 is negative 4. Negative 4 times negative 4 is 16. And let's see. 4 divided by negative 4 is negative 1. Okay, got it. And negative 4 is less than negative 1. Owing 4 is definitely lower than, or you have less money than if you owed $1. So again, from 1 to here to 6, we see that we had to reverse the inequality in order for it to be true. And now let's look at number 8. So I'm noticing if we multiply by a negative and we divide by a negative, we have to reverse the inequality in order to be true. What happens if we divide by a positive? Will that make it reverse? So divide each side by 8. Well, there are 2 sets of 8 and 16, so that's 2. And 4 is half of a set of 8, so 4 divided by 8 is a half. And I see that 2 is greater than a half. So it looks like the same is true. The same inequality holds when we divide by a positive 8. So it looks like it's really all about dividing or multiplying by a negative. And it wasn't really about adding or subtracting. It didn't even make a difference. We could have added a negative, I don't know, add a negative 2 and add a negative 2, we would get 14 and 2, and it would still have the same inequality of greater than in order to be true. So it really is boiling down to multiplying and dividing by a negative when we need to be careful. So additive properties, and remember in our recall we talked about the additive property for equations or equality, and now we're doing it for inequality. And it appeared that if we added or subtracted the same amount for both sides, we're good to go. So add or subtract same from both sides of any one of these inequalities. And yes, I realize that in this example we only did this, but if you started this whole example and you wrote 4 is less than 16 and you did all of this, you would have the same conclusions over here. Okay, so add or subtract the same amount from both sides of the inequality symbol, and the same inequality will be true. It maintains the validity of that inequality. But now the multiplicative property gets a little bit fuzzier because we have to make sure we put in this case, this weird scenario. So, okay, if we multiply or divide by the same on both sides, okay, of the inequality, then the same inequality is true. Okay, but there's a but. Okay. Multiply or divide by a negative. So scale up, scale down by a positive on both sides. Uh-oh. I should have said same positive row. I'm going to add that in right now. Pretty important. Multiply, scale up or scale down by the same positive on both sides, then the same inequality is true. But multiply or divide by the same negative, right? And be sure to reverse the inequality to be true. So then reverse the inequality to be true, okay? And this is going to come in handy for scenarios like we saw in example 1. So remember, in example 1, we don't really know what value x is taking on, whether it's going to be positive or negative. In example 1, it was positive, and we just plugged it in and we found out if it was true or not. But we might not know what value x is taking on. And if we multiply or we divide or we add or subtract these, I mean, if we add or subtract, whether it's a positive or negative, we're good to go. That's okay. But if we start multiplying and dividing on both sides, we have to be careful. We have to reverse the inequality. Okay. It's true that in the next example, in the next video, we're going to start with example 3. But I do want to mention a couple things that my students normally ask me when they are actually in my presence. Okay, so students of the past have asked me, what happens, okay, if you take the reciprocal? So if we look at 2/3 being less than 3/4 and we take the reciprocal of both sides, then we see we have 1.5. So the reciprocal of 2/3 is 3/2, which is 1.5. And the reciprocal of 3/4 is 4/3, which is 1 1/3. And 1/2 is more than 1/3, so 1.5 is more than 1 1/3. And notice when we took the reciprocal, it actually reversed the inequality. Okay, I know that a lot of people talk about multiplying and dividing by a negative, but this is true too. We have to be very careful when we do operations with inequalities because it could quickly change directions. After this, they usually ask me about squaring both sides. I will leave that to you. Try squaring both sides and see what would happen if you would have to leave it the same to be true or if you would have to reverse it to be true. Nonetheless, in the next example, in the next video, we will look at the next example.